All right, welcome to the first screencast for the nomenclature unit, which just means naming. It's a fancy word for naming. We are going to write and name, or write formulas and name various different compounds, binary, ionic, molecular, acid compounds, but we're also going to deal with polyatomic ionic, polyatomic acid, and polyatomic base compounds. So by the end of this unit, you're going to have a fairly good idea on how to name and write formulas for a whole bunch of different types of compounds. This is just like a basic little chart, summary chart for you. We're going to start off with just the basics of compounds, ionic versus molecular. We're going to deal with ionic compounds, which if you remember, are between a metal and a nonmetal. And then have a single oxidation state, ones that have multiple oxidation states. You know those ones I said we were going to ignore last unit. Well, those are now going to come back to haunt us. And we're also going to talk about acids and bases, but only the strong ones. We're not going to deal with much in terms of acids and bases. And then how to name molecular compounds, which are, nonmetals bonded together. So our first two objectives we're going to cover together, which is just identify the charges of monoatomic ions by using the periodic table. You've already done this before. This is what you labeled on your periodic table when you were labeling your valence electrons and your oxidation numbers. And we're going to describe the system that IUPAC has designated for naming positive and negative ions, and we're going to write the names and formulas of each. So our essential question is, how are positive ions and negative ions named? So we're just going to go ahead and start. So naming ions, we're only going to deal with inorganic compounds in this unit. We are not going to deal with carbon or carbon-containing compounds that you might have seen a lot in biology. We will specifically cover those in our organic chemistry unit. But there are 9 million named inorganic compounds, so we have plenty to work with. Many have common names as well, which is why some sort of a system had to be developed. The common names are not very useful because they're not standardized. Acetic acid is the technical name for vinegar. Calcium oxide is the technical name for lime. Mercury is sometimes referred to as quicksilver. You may or may not have heard it referred to as that before. Hydrochloric acid is muriatic acid or battery acid. My father calls it muriatic acid. I know people that think that battery acid is hydrochloric acid, but in reality, battery acid is sulfuric acid. So you can already see where there's some issues with the common names. It's kind of like having a naming system in biology for all the species and all the life on Earth. It's a consistency thing. So the naming system was developed in about 1921 by IUPAC, the International Union for Pure and Applied Chemistry, and they just kind of set up these basic rules. So the first thing that we use, and we have been using, the formula for an element is its symbol. So if I want to write the formula for fluorine, I just write F. If I want to write the formula for carbon, I write C. That's what's nice about knowing the symbols. And don't forget about those 7 diatomic molecules. You should have them labeled on your periodic table, but the nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen, remember, when they're by themselves, they exist in pairs. So as N2, O2, F2, Cl2, Br2, I2, and H2. This is also a review for you. A charged atom is what we call an ion. We have cations and anions. So we have positive ions, we have negative ions. You're going to see this symbolism a lot because in an ionic compound, the cation is what you write first, and the anion is always what you write second. That's just some nice symbolism and just a nice system that we use to keep everything in line. So you'll always put the metal first and the non-metal second. So here's our monoatomic ions. Here's our naming rules. How do we name the positive ions? How do we name the negative ions? Monoatomic because it means one atom. Mono equals one. So the symbols and the names. When you finish with this slide, I want you to write a level 2 test question on the side of your notes in relation to how to name cations and anions. So you've already learned how to write the symbols. We're going to start with cations. You've already learned how to write the symbol for a cation. You literally just write the element symbol and then you put a charge as the superscript. So here I have Mg2 plus, Al3 plus, Na1 plus, and you'll notice these are the oxidation numbers that come from their valence electrons on the periodic table. You already have them all labeled. The naming rules are pretty simple for these. The name is the same as the parent element, and then you just literally add the word ion to the end of it. So instead of having magnesium, I have magnesium ion. Instead of having aluminum, I would have aluminum ion. Instead of having sodium, I would have sodium ion. So naming a positive cation is pretty easy. You don't have to do anything to it except add the word ion to the end. Now, if I had Mg with no 2+ charge on there, I would literally just call that magnesium. When I have it as the charge, when it has lost 2 electrons, I now have magnesium ion. Anions are a little different in how you have to change their name a little bit. But you've heard these before. This is not foreign to you. You just didn't know why they were this way. So an anion, we've written the symbols for them. You write the symbols just like normal, like we've always done, where you take the symbol for the element and you put the charge on it. So chlorine 1-, oxygen 2-, nitrogen 3-. You write the charge as a superscript. The naming rules for these, you're going to use the stem or the root of the parent name, and you're going to just change the ending to IDE to show that you have the ion. You don't need to add the word ion to the end of it, because by changing it to IDE, that implies you already have the ion. So instead of calling Cl1- chlorine ion, or chlorine if it was the atom, I now call it chloride. I changed the ending to IDE, which is why sodium chloride is called that. Table salt is called that. So oxygen 2- is oxide. So I change the ending. I keep the root of the parent name, and I change the ending to IDE. Nitrogen is nitride. So I've just taken that stem, and I've changed the ending to IDE. You're going to get a lot more practice with this as time goes on. I'm just introducing this to you now. So remember to write your level 2 test question on the side of your notes. So here's some simple compounds, because now it's great to know how to name an anion and it's great to know how to name a cation, but we have to be able to put these things together. So this is a little bit of foreshadowing for you into what we're going to do in the future, probably in the next class period, but I just wanted you to see a little bit on where this stuff goes together at. If you know the symbol or name of the element, which you should because it's all listed on your periodic table, and you know the charge it forms, this is the key. If you know its oxidation number, which you should for everything that's in the column 1, column 2, column 3, and then all those nonmetals, you know their charges. You can write basic formulas and names. For these examples, I'm just going to give you standard examples of ionic compounds, which means it's a metal and a nonmetal. You always write the metal first, so remember that dividing line on your periodic table. You're going to put the metal first and then the nonmetal second. That is the standard format that we will always use for an ionic compound. It'll always be the cation, then the anion, or the positive ion, then the negative ion. When you are writing the formula for these, the most important thing for you to remember is that your charges must balance out. If I have 5 positives, I have to have 5 negatives. Your number of positives and negatives must balance to 0. And that is going to allow your compound to have a neutral charge. In an ionic compound, you have something that is positive bonded to something that is negative, and you have to balance them out. So, warning, big difference here. There is a big difference between a superscript and a subscript. The superscript is raised. That's what we use to tell charges of ions with. And the subscript, which is lowered, is what we use to tell number of atoms. So this tells me that the charge of calcium is a 2+. This tells me that I have 3 chlorine atoms bonded to 1 atom of beryllium. So superscripts and subscripts tell you 2 totally different things. This tells me that calcium has lost electrons. And this over here tells me that the beryllium atom bonds with 3 chlorine atoms. So you need to make sure and use superscripts and subscripts correctly. So just a little bit of warning. So here's some examples, and we're going to work out a bunch of these examples in class. This is what you're going to spend the whole block doing, is just working out practice problems. So my first example I'm going to take you through is sodium chloride. Notice I named the cation just as its regular name. The anion, I changed the ending to IDE. So I have sodium and chlorine bonded together, forming sodium chloride. Well, if I look on my periodic table, sodium's in the first column, so it has a 1+ charge. And chlorine is in the second to last column, so it has a 1- charge, just by using my valence electrons. This is what we learned in the last unit. So they're already balanced. I have a 1 positive and a 1 negative, so I don't have to do anything fancy here. I just literally now write my formula. I have 1 sodium atom for every 1 chlorine. The next one's not quite as easy. Calcium fluoride. Calcium, if I look on my periodic table, is in the second column, so it has a 2+ charge. Fluorine has a 1- charge. Well, obviously 2+ and 1- are not the same, and I have more positives than I have negatives. So I actually have 2 positives and I have 1 negative. So I need to get the same number of negatives. In order to do that, I now just have 2 fluorines instead of 1. So I have calcium, that's a 2+, and I have fluorine, that is now a 2- because I have 2 of them. So my formula for this one is CaF2, and I have to put the subscript 2 there to show I have 2 fluorines. The last example I'm going to take you through here is aluminum oxide. Aluminum, if you look on your periodic table, is a 3+ charge. It's in the 3+ column. And oxygen is a 2- charge. Well, clearly, so aluminum has a 3+, oxygen has a 2-. I have to get these numbers balanced. 3 is never going to equal 2, and 2 is never going to equal 3. So what I have to do is find their least common multiple. The least common multiple of 3 and 2 is 6. So I have to try to get the positives to 6 positives, and I have to get the negatives to 6 negatives. To get both the positive and the negative to 6+ and 6-. Well, what can I multiply 3 by to get to 6? 2. So I need 2 aluminums to get to 6+, which is why I put 2 aluminums down here. Oxygen, I have a 2- charge. What do I need to multiply it by to get to 6? 2 times 3 would be 6. So I need 3 oxygens, which is why I put 3 there. So if this has a 3+ charge and I have 2 of them, I have 6 positives. This has a 2- charge. I now have 3 of them. I have 6 negatives, and they've now balanced each other out. So we're going to work out more examples in class. I wanted you to get these 3 examples down in your notes. We will work out more examples in class and then try to complete these on your own. These are the ones we're going to do together in class. Sodium bromide, potassium sulfide, potassium oxide, beryllium phosphide, sodium oxide, barium sulfide. Notice the symbolism used in their names. Work them out just like we did these previous practice problems, and that's what we're going to do in class, and then you're going to spend the whole block working on practice problems. The summary for this particular objective is going to be in a 3-2-1 format, but we will do that in class.